Assalamualaikum warahmatullahi wabarakatuh. We from group KSB, and now we want to present the application of partial differential equation in interest rate model used by bank. So this is our group members. So for the introduction, partial differential equation show the relationship that involve the rate of different function, variation from one variable to other. When it comes to financial modeling, partial differential equation essentially consider evolution in time under uncertainties connected to financial instrument. By solving this equation, analysts can state price, risk hedge, and optimize portfolios in dynamically roaming markets. So the presenting objective is addresses the fundamental role of partial differential equation in financial modeling by deeply analyzing their use in interest rate models from theoretical and practical benefits. The aim is to present how institutions can utilize this equation to make informed decision in pricing, risk management, and market operation.
So, for this part, I will tell you about why exactly we choose RStudio as our programming software. RStudio is an integrated development environment specifically designed for R programming language. It is widely used in fields like statistics, data analytics, and numerical computation because it is both free and open source, making it a cost-effective option for students and professionals alike. What sets RStudio apart is its user-friendly interface, which simplifies coding and debugging, and its strong package ecosystem such as DSolve, which is ideal for solving differential equations. Additionally, its powerful visualization tools like ggplot2 enable us to create high-quality graphs to interpret and present numerical solutions effectively. This makes RStudio an excellent choice for our project, especially when solving and visualizing partial differential equations. For this slide, I will tell you about the relevant R packages for PDEs and also key interface in RStudio. To solve our partial differential equation, we use specific R packages that streamline the process. The resolve package is a core tool for solving both ordinary and partial differential equations. For visualizing results, we rely on ggplot2, which produces detailed and customizable graphs. We also use Pragma for additional numerical computations and Reshape2 to format our data for easy plotting. These packages together make RStudio a comprehensive platform for our analysis. Next is the key interface in RStudio. RStudio is organized into 4 main panels, each designed for specific tasks. The first is the source panel, located at the top left. It's where you write, edit, and save your R script. It features syntax highlighting to make code more readable and tools for debugging. Next is the console panel. At the bottom left is where commands are executed. This is where you can quickly test lines of code and view real-time results, including error messages or warnings. Next is environmental panel on the top right. It tracks all objects, datasets, and variables loaded in your session. It is essential for managing and monitoring your workspace efficiently. At the bottom right is the files, plots, packages hub panel, which is multifunctional. You can browse local files in the Files tab, view and export visualizations in the Plots tab, manage packages in the Packages tab, and access detailed documentation in the Hub tab. And finally, the toolbar at the top offers quick actions like running scripts, saving files, restarting sessions, or importing datasets. This intuitive interface streamlines your workflow, making RStudio both powerful and user-friendly.
Next is differential equation problem. So let's start with the Cox-Ingersoll-Ross CR model, which is widely used in the finance to model how interest rates evolve over time. This model is built on a stochastic differential equation, which means it includes both deterministic and random components. The key idea of the CR model is the interest rate don't just move randomly, they tend to revert toward a long-term average level called theta. This is what we call mean reversion. At the same time, the model accounts for the unpredictability of real-world financial markets by incorporating randomness through a winner process. The mathematical equation for the CIR model is as follows in the slide. Here what each part mean. RT, this represents the short-term interest rate at any given time. K, this is the speed of the reversion. It tells us how quickly the interest rate moves back toward its long-term average theta. Theta, this is the long-term average or equilibrium level that the interest rate hovers around over time. Sigma, this is the volatility or how much randomness is added to the interest rate change. DWT, this is a winner process or a random shock which models the unpredictable movement in the market. The interesting feature of the CIR model is the square root term. This ensures that the interest rate can never drop below zero, which is a major limitation of some older models like the Vasicek model. Okay, when we use the CIR model to price financial instruments like bonds, we translate it into a partial differential equation or PDE for the bond price, which can be shown below. This equation combines time derivative, randomness through volatility, and interest rate dynamics. The boundary condition for solving this PDE is typically V RT equal to 1, which means that at maturity T, the bond pays a value of 1 unit, for example 1000 ringgit for a zero coupon bond. Solving this equation numerically help us find the bond's price at any point before maturity. So, why do we use CIR model? The first one is non-negative interest rate. The square root term makes sure the interest rate can become negative, which aligns with real-world expectation. The second one captures real-world behavior. Interest rate don't just wander aimlessly, they tend to revert to a long-term average. The CIR model reflects this mean reverting nature. The third one is flexibility for various financial tools. It used in pricing bonds, derivatives like swaps and caps, and even in building forward-looking yield curve. So, the next part is real-world application. Banks use the CIR model in several ways. For the first one is bond pricing. For zero coupon bonds, the CIR model helps calculate the present value of cash flow based on dynamic interest rate. Next is risk management. Banks use it to estimate how sensitive their portfolio are to change in interest rate. Next is yield curve modeling. By calibrating the model to current market data, banks can generate a forward-looking yield curve, which is essential for decision making. Lastly is derivative pricing. The model is also applied in pricing interest rate derivatives like caps, floors, and swaps. The CIR model is powerful because it combines mathematical rigor with real-world applicability. It's not only the model, the randomness of the interest rate, but also their tendency to revert to a stable average. To solve the CIR model, we often use numerical methods, as solving the stochastic differential equation analytically is complex or sometimes impossible for certain conditions. Here we are applying the Euler method, which is a straightforward numerical technique. It helps us approximate the solution of the CIR model over small time steps, delta t. Let's start with the drift term in the CIR model equation, k in the bracket delta minus RT dt. To approximate this, we replace the infinitesimal time step dt with a small time interval delta t. This represents the deterministic part of the rate change, meaning how the interest rate reverts to the long-term average, theta. Next, we have the diffusion term, which introduces randomness to the model, sigma square root RT dWt. Here dWt is a winner process or a random shock. To simulate this, we replace dWt with delta Wt. This means delta Wt is drawn from a normal distribution with a mean of 0 and a variance of delta t. This gives us the updated diffusion term of sigma square root RT delta Wt. So, to find the new interest rate RT plus delta t, we combine the approximate drift and diffusion terms. The Euler approximation formula becomes as shown below. This equation let us calculate the interest rate at the next time step, t plus delta t based on the current interest rate, RT, the deterministic drift and the random diffusion. While the Euler method is simple and effective for small delta t, it has limitation. First one is numerical inaccuracy. Using larger time steps may lead to instability or error in the solution. The second one is negative interest rate. If RT becomes negative, the square root becomes undefined. This isn't physically meaningful, so modification like truncating RT at 0 or reflecting it can be applied.
For defining parameters, first we have the parameters A, B and sigma. These are specific to the model and dictate how the interest rate behave over time. A is often referred to as the mean revision speed. It controls how quickly the interest rate reverts to its long-term average. For B represents the long-term average level of the interest rate. It's where the model expects the rate to stabilize over time. For sigma, the volatility determines how much the interest rate fluctuates randomly. A higher value means more uncertainty and larger swings in the rate. Next, we have R norm, the initial interest rate. This is the rate at the starting point of our simulation, or at time t equal to 0. It's crucial because it sets the starting condition for our model and influences how the simulation evolves. The parameter dt is the time step size in our numerical simulation. Think of it as the resolution of our model. Smaller values of dt give us more precise result because we are capturing finer changes in the interest rate. However, there is a trade-off. Smaller time steps means longer computation times. Moving on, we have t, the total time horizon. This represents how far into the future we want to stimulate the interest rate. For example, if we set t to 5, we are looking at the rates of over 5 years. Finally, we calculate the numbers of steps, n, using t over dt. This tells us how many time intervals are needed to cover the entire time horizon. For instance, if t is 5 and dt is 0.1, we will have 50 steps in our simulation. For the next point is initializing variable. First, we create a sequence of time points which we call time. The sequence starts at 0, representing the beginning of our simulation, and goes up to t, the total time horizon. The time points are spaced by dt, the size of the time step. For example, if t is 5 years and dt is 0.1, we will have time points like 0, 0.1, 0.2, and so on, up to 5. This gives us a clear timeline for our simulation. Next, we initialize a vector r to store the stimulated interest rate. This vector will hold the interest rate value for each time point in our sequence. The first value in our interest rate vector R1 is initialized to the starting interest rate R norm. This is the rate at time t equal to 0, which serves as the starting condition for our simulation. For instance, if R norm is 2%, then R1 is set to 0.02 in our vector. For the next point, simulating the CIR model using Euler's method. The mean revision term pulls the rate towards its long-term mean. The random term adds realistic fluctuation. Combining this term gives us the change in rate dr, which is added to the previous rate to compute the new rate. This step-by-step approach using Euler's method allows us to stimulate the behavior of interest rates under the CIR model. How the codes R actually works. It initializes the variables and sets up the parameters. It also stimulates the interest rate step-by-step by calculating the mean revision and random terms. Finally, it generates a plot to visualize the result, showing how the rates evolve over time. This approach gives us a clear and detailed simulation of the CIR model. The figure shown beside is the code for the CIR model by using Euler's method in RStudio.
Next, we go to the result and analysis. This part we divide by 3. The first part is graphical representation of solution. The graph shows the evolution of the interest rate over time based on the CIR model, simulated using Euler's method. The interest rate starts at an initial value 0.03 and fluctuates over time, displaying mean reverting behavior.
The stochastic nature of the process introduces short-term volatility, while the mean revision parameter ensures the rate does not deviate significantly from a long-term average. The second part is interpretation of results. Behavior of the model also divided by three components. The first component is mean revision. The CIR model reflects the real-world tendency of interest rate to revert to a long-term average. This is apparent from the oscillation around a central value. So the second component is volatility. The amplitude of fluctuation highlight the impact of the volatility factor in the CIR model, where larger volatility increases the randomness in the path. And the third component is application. This model can be applied to pricing interest rate derivative, bond pricing, and risk management in finance. The simulated paths are useful for Monte Carlo method in financial modeling, where multiple trajectories are averaged to estimate prices or probabilities. And the last aspect is a validation of the model. Theoretical validation. The CIR model is well established for capturing the dynamic of interest rate. It incorporates economic intuition, such as mean revision and volatility, in a mathematically consistent framework. Euler's method, while simple, is effective for providing an approximate numerical solution. However, care must be taken to ensure small time steps to maintain stability and accuracy. And the last one is empirical validation. The CIR model's parameter should be calibrated using historical interest rate data. Calibration ensures the model captures market-specific behavior. A comparison of the simulated trajectories with actual historical interest rate can validate the model ability to replicate real-world dynamics.
To conclude, partial differential equations are very important in financial modeling because they help to understand and predict the behavior of financial instruments. They are widely used in interest rate models such as Black-Scholes, Fast-Check, and Whole-Wide for pricing derivative, managing risk, and guiding investment decision. So the overall order is to let partial differential equation allow financial firms to manage uncertainty and hence perform better in decision-making process. However, the numerical methods offer the solution to complicated financial models and flexibility to take actual characteristics such as fluctuating volatility and time-varying parameters into account. By adopting some simple approach, they may provide effective approximation and make it possible to treat many cases in which an exact solution is unfeasible. This method rely on precise input parameters, as small deviation may cause result to be unstable. While these caveats cannot be ignored, it is a big plus point that numeric method remain a very effective tool in financial modeling. So that's all from us. Thank you.